I'd like to thank the LISI 2024 conference organizers for inviting me to present my paper, Varicella Vaccination as a Potential Multiple Sclerosis Prevention Strategy. Okay. This presentation will cover the following things on the screen. My background is I have a PhD in microbiology and immunology from Temple University, and I did a postdoc at Thomas Jefferson University, both in Philadelphia. I have 20 years of research experience at the bench, and some of that was multiple sclerosis research. My sister had multiple sclerosis. She was diagnosed in 1986, and that's why I had developed an interest in that topic. She suffered with the disease for 23 years, and I don't want anybody else to get this disease, and so I was captivated by this huge puzzle. I'm going to now discuss multiple sclerosis. Then I will state the hypothesis that I'm presenting in the paper and present a step-by-step rationale for the hypothesis, explore methods to test the hypothesis, highlight implications for MS prevention and treatment, and conclude with a call to action for testing the hypothesis as quickly as possible. What is multiple sclerosis? It is a chronic, non-contagious disease affecting the brain and spinal cord in humans. Symptoms include vision problems, muscle weakness, spasms, fatigue and tingling, and other problems. MS affects 2.9 million people worldwide and can progressively worsen, impacting quality of life. 1 in 3,000 people globally gets MS, but in high-risk MS regions, 1 in 300 do. Despite over 150 years of research, the exact causes of the disease are unknown, but are believed to result from a combination of genetic and environmental factors. These factors trigger a pathological process that destroys the myelin. It's an inflammatory process. The myelin insulates neurons in the brain and spinal cord and helps them transmit electrical signals efficiently. When you destroy the myelin, then they can't transmit the signals well. You'll see in the next slide a picture of one MS patient's brain. There are 2 MRI images there. On the left is a T2 weighted image, and on the right is a T1 weighted image, for those of you who know a lot about MRIs. The left image shows one cross-section of the brain where you can see white areas with black arrows pointing to those. Those are very active lesions in the brain. They are full of inflammatory cells, and there's edema going on, and they're destroying the white matter of the brain, the myelin in the brain. And on the right side, those same arrows, the black arrows, are pointing to where the tissue has been destroyed. You can see the gray areas that were underneath those lesions, or among those lesions, and that's the type of damage that you see in MS. And that can happen in the spinal cord as well. MS lesions fluctuate over time. I was going to show you the video and the link, but it didn't work when I tested it with another Zoom user. So I just point you to this link at www.msdiscovery.org. And it shows one MS patient's brain over the course of a whole year. They have a whole set of scans, and they compiled a video that shows you how the lesions come and go throughout the whole year. And the video shows the lesions in different parts of the brain growing and shrinking, and they're not coordinated with each other or synchronized in any way. So you'll just see that one lesion will grow and shrink, and then another lesion will start again in a different area, growing and shrinking. So it's a very interesting video, and it gives you an idea of what's going on in the brain of an MS patient. Features of MS include the onset of the disease typically occurs between ages 20 and 50, peaking around age 30. That's the age that my sister was when she got MS. MS affects women more than men. The ratios can vary from 1:1 to 4:1 in some regions and populations. MS is most common in Caucasians, but may be increasing in other groups. And concordance and identical twins, which means concordance is if the two twins have this, both have MS, is at most 30%, indicating a significant role for environmental factors in the disease causation. Prevalence rates can vary widely across the globe. Rates increase with increasing distance from the equator, which is known as a latitude gradient of MS prevalence. This gradient may be disappearing now, but in the 20th century, it was considered the norm, a normal feature. Fewer than 25 cases per 100,000 people have MS in Asia, South America, and Africa. Rates approaching or exceeding 300 cases per 100,000 are found in Scandinavia, Germany, Italy, and North America. And this is all from the Atlas of MS, which I'll show you the link to in the next page. MS prevalence rates in certain regions have increased dramatically, including Japan and Denmark. And this has happened within a few decades. So if you want to see a map of the MS prevalence and be able to see the prevalence in the specific countries, you can go to the site atlasofms.org site shown on the screen, and that will show you the most recent prevalence data for each country. And the prevalence in North America is approximately 288 per 100,000. In Germany, it's also high. In Italy, it's high. And Scandinavian countries are high. And the highest rate that I've ever seen was Sardinia, which is an island off of in Italy, and that was 330 per 100,000. Clues to MS causation include infection hypotheses, migration studies, changing MS rates in various regions, and environmental triggers. Infection hypothesis I'll discuss is based on two things: MS epidemics in the Faroe Islands that were reported a few decades ago that happened during World War II, and studies linking delayed Epstein-Barr infection, Epstein-Barr virus infection with MS. Those will be discussed shortly. And migration studies show that MS risk varies with age at migration and the original location of the person and the destination country where they end up living. Changing MS rates have been seen in different ethnic groups, including African Americans. They believe that has increased dramatically, although some think that data is controversial. Environmental triggers indicate that at least two environmental triggers trigger the disease, with childhood trigger linked to MS. The first triggers thought to occur in childhood, likely a common infection. The World War II, there was an epidemic of MS in the Faroe Islands I'll discuss, and that's one of the most pivotal studies showing this infection-based risk. MS case clustering by birthplace and age. Children who grow up in a high MS risk area and live there when they're very young, if they move away and get MS later, the cases that get MS can all be traced back to that location and the young age of the children that were near each other in that place. So it seems like that's convincing evidence there could be some sort of infectious cause. MS risk is influenced by migration age and location, as I discussed. Rising MS incidence in non-European countries is being observed, as well as some European countries, such as Jordan and Iran and Turkey. They're noting higher MS rates. Some of that may be due to better diagnosis, though. The first, as I said, the first trigger was a childhood factor, and the second trigger is likely delayed Epstein-Barr virus infection. That means that this virus usually infects children at very young age, except in countries that are industrial countries or the modernized water systems and things like that with higher hygiene. That's not a good thing because delayed EBV infection is probably not the norm, but is an unusual situation of modernization. Anyway, this has been implicated in MS. The best study is the first one. It was a large longitudinal study showing antibodies against EBV appear shortly before MS onset in military recruits. They had 10 million recruits, and they were studying those who did not have prior exposure, and noticed that they followed them over several years by collecting blood samples and measuring the antibody levels. And sure enough, a lot of them, a significant number, developed MS shortly after they seroconverted to EBV positive antibodies. The second is a large study of patients with early MS. They have significantly high EBV antibody rates compared to controls, healthy controls. Infectious mononucleosis is linked to increased MS risk. MS is rare in countries where Epstein-Barr virus primarily occurs in very young children. And if people do not have EBV antibodies and were never exposed, their MS risk is very low. What is EBV infection? EBV infects over 95% of people worldwide by age 50. The infection in children is generally asymptomatic, but in adults and adolescents, it can cause serious illness, infectious mononucleosis, which is linked to MS. In countries with low MS rates, EBV infection occurs predominantly in young children. In countries with high MS rates, 30 to 50% of infections occur in adolescents and adults. These observations suggest that early childhood residence in regions with low MS rates may lead to exposure to a protective factor against MS, which may be Epstein-Barr virus. Due to substantial evidence suggesting the second MS trigger is likely post-childhood EBV infection, the remainder of this talk will present step-by-step rationale for the hypothesis that the first trigger is varicella infection caused by a type of varicella virus known as clade 3, VZV, which is the virus that causes varicella. Evidence that the first MS trigger is a respiratory infection is key to the hypothesis. The most crucial information related to this assertion is that in World War II, the Faroe Islands epidemic, there was an extensive study conducted in the 1970s through the 1990s by John Kurtzky and Ann Heltberg, conducted there to determine the cause of MS. The Faroe Islands is an isolated cluster of 18 islands in the North Atlantic. In April of 1940, thousands of British troops landed and occupied the island until 1944. Before 1940, there were no MS cases on the island. However, beginning in 1941, the incidence began to increase, peaking at 10 cases per year by 1944, with a total of 21 cases comprising the first outbreak. 3 additional MS outbreaks were observed at 15-year intervals after that first outbreak concluded in the 1950s. Locations of troop encampments across the islands were closely tied to the residences of MS patients in the first outbreak. The study concluded that asymptomatic British troops transmitted unknown widespread infectious agent to the Faroese population during World War II. These findings indicate a respiratory virus that can remain latent in the host after recovering from the initial infection. And that way it may cause MS. The first MS trigger is likely a common respiratory virus that remains latent in the host. The widespread nature of the Faroese outbreak implicates a respiratory virus in MS causation. The 15-year intervals separating the 4 MS outbreaks suggest they were caused by a virus that can remain latent, then reactivate years later to start a new infection cycle. It could be a retrovirus or a herpes virus, possibly an adenovirus. Retroviruses and most herpes viruses are spread through intimate contact, not through airborne transmission or through exchange of blood. Only one herpes virus is spread by the respiratory route. That's Varicella-Zoster virus. Therefore, the first MS trigger is likely Varicella-Zoster virus infection, which causes chickenpox, also known as varicella. What is varicella? It is a contagious infection caused by Varicella-Zoster virus, spread through contact or with lesions of a person who has infected, their skin has lesions, or inhalation of virus. Initial infection causes flu-like symptoms and red skin lesions that contain infectious virus, leading to outbreaks typically in households and schools. Infection predominantly occurs in children younger than 10 in temperate climates. In the tropics, it frequently occurs in adolescents and adults, with high adult susceptibility rates observed in the tropics. Recovery from infection generally confers lifelong immunity from reinfection, but the virus remains in the host in latent form for life. VZV reactivation, though, can occur decades after the initial infection, causing shingles, generally in people over age 50. A 2-dose varicella vaccine was administered in several countries since the early 2000s, but shingles vaccines for older adults are also available. Support for VZV infection as an MS risk factor. High MS rates in countries with high childhood varicella rates have been noted. They tend to be in temperate regions located far from the equator. Lower varicella seroprevalence and MS rates in Canadian Hutterites, it's a religious sect, isolated sect in that country, compared to the surrounding population. So lower varicella and low MS rates seem to go hand in hand. Detection of VZV DNA in white blood cells of MS patients during disease relapses, but not during remission, and higher quantities of the viral DNA in those cells versus controls demonstrate, despite the similar antibody levels, also are evidence in support of VZV as an MS risk factor. Furthermore, there's increasing rates of VZV and MS in Mexico, so that they go hand in hand there. Higher VZV seroprevalence rates in MS patients of 98% versus controls 85% in northern Jordan, a country with rising MS rates. And finally, this virus can infect the oligodendrocytes. They're the cells that produce myelin in the brain and spinal cord, and those are the cells targeted by MS. There is one additional point I have to make, that varicella, though, it infects nearly all children in Japan, where MS is rare, as well as in Northern Europe, where MS is common. These regions have similar high delayed EBV rates, suggesting these VZV viruses are not all the same. So that point is important. Not all varicella viruses are the same, as shown in the early 2000s. Varicella is caused by at least 5 major Varicella-Zoster virus types. They're known as clades, and they're numbered 1 through 5. VZV clades 1 and 3 are predominant in Europe, where MS is common. Clades 2, 4, and 5 are prevalent in Asia and Africa, where MS is rare. If VZV causes MS, either clade 1 and/or clade 3 is most likely the MS trigger. However, MS is much less common than varicella, even in regions with highest MS rates, suggesting that at most one of these clades is linked to MS, not both. So which clade is it, clade 1 or clade 3? An extensive literature review gave you very little information on the clades infecting MS patients. But I did find one paper describing a single MS patient who was infected with clade 3. They had shingles. They took the shingles lesion and they genotyped the Varicella-Zoster virus there, and it was clade 3. This finding led to the hypothesis that VZV clade 3 may be involved in MS causation. So putting it all together, the proposed hypothesis is that MS is caused by 2 environmental triggers: childhood varicella infection caused by clade 3 VZV infection, the first trigger, and delayed EBV infection, the second trigger. To test the hypothesis, it would be, one way would be to genotype VZV isolates from more MS patients with exclusive detection of clade 3 supporting the hypothesis. Alternatively, it's possible that the varicella vaccine, which is clade 2, might prevent clade 3 infection if administered early enough. And that vaccine is administered to infants right now, up to age 15 months, and then they give a second dose later, I think around age 6 in some countries. Not sure about all the countries, but that one, monitoring MS rates in populations receiving the clade 2 vaccine, which countries have been administering since the early 2000s, may cause decreasing MS rates noted by the year 2035-ish, I would say, mid-2030s. Countries that have been doing this include the US and Canada, and then parts of Italy, specifically Sicily. Additional support for the hypothesis can be found in a 2013 study showing 80% of 23 varicella cases in Sicily, a region with extremely high MS prevalence rate, were infected with clade 3 varicella, the zoster virus. The other evidence is before varicella vaccination was practiced, Japan had extremely high childhood varicella rates of clade 2 and very low MS rates, despite a high delayed EBV infection rate resembling rates in high MS countries such as the US and Germany. Thus, it indicates perhaps childhood clade 2 VZV infection may prevent MS by preventing clade 3 infection, which is the trigger. Predictions of the proposed hypothesis include that the sequence of these two infections is crucial, whereby clade 3 VZV must be contracted before EBV to see MS occur. Factors increasing early VZV infection and late EBV infection rates should increase MS risk because those two factors would ensure that the proper sequence occurs to induce MS. Whereas the opposite sequence would prevent MS, early EBV infection prevents MS. Competition between clade 3 and other clades may prevent clade 3 infection or reduce clade 3 infection rates, reducing MS rates. Immigration bringing VZV clades 1, 2, 4, or 5 into a region with high MS rates may reduce MS risk decades later, when the children who contract those new clades are the peak MS age around 30. Finally, varicella vaccination with clade 2 should prevent MS if the hypothesis is correct. So if the hypothesis can be confirmed, varicella vaccination should be considered in countries without vaccination programs, especially if they see rising MS rates there. Given that VZV and EBV are herpes viruses that can remain latent after initial infection, drugs that prevent their reactivation may slow disease progression in existing MS patients. And finally, early childhood EBV vaccination should be explored as an alternate strategy for preventing MS, which has been proposed by Alberto Schierio's group, and they've been working on that vaccine. A call to action. It is my hope that someone with VZV isolates from a large number of MS patients will genotype them to quickly test this hypothesis to warrant varicella vaccination to prevent future MS cases. I'd like to acknowledge a lot of people. First, the organizers of this conference, thanking them for the opportunity to present my research to such a wide audience. I'm also grateful to my husband, Nelson, for his unwavering support in the preparation of this paper and presentation, and to my sister, Carrie, for her help proofreading earlier drafts. I also extend my thanks to the many thousands and thousands of MS researchers whose invaluable contributions to the literature have informed and inspired my work over the past 38 years. And finally, I'd like to extend my sincere thanks to everyone who attended this presentation. Thank you.
Thank you so much for your presentation. It was indeed very interesting. And if anyone has any questions